It's the
Good.
Weston and Southfield.
Okay, I'll get out of the way then.
MUG,
Turn it over to
November
Will.
2013.
All right, so this talk is going to be a pretty quick talk, 15, 20 minutes. If we have a little bit extra time, might get into some demos, be a little bit longer. The talk is about Clojure, which is a programming language, a functional programming language that was invented in 2007. And it's been gaining a little bit of popularity as it's been going. So Clojure is a modern Lisp dialect. It's designed to be hosted and includes simple concurrency constructs. So that right there, that's a pretty dense sentence, right? You kind of look at that, your eyes start to glaze over, right? So we're going to break down into three main areas, right? We're going to talk about what it means to be a modern Lisp dialect, how it's designed to be hosted, and then we're going to go into some of the concurrency constructs that are built right into Clojure. So first, what the hell is a modern Lisp dialect, right? So some of you probably know Lisp is a very old programming language. It was, I think, late 1950s, early 1960s, around that time when the original Lisp came out. And since then, it spawned all sorts of different versions of Lisp, sort of variations, and these variations are called dialects. So there's two main Lisp dialects you'll see out in the world today. You usually see Scheme, which is more of a sort of academic language, right, or more sort of like an educational language. You see it mostly used in like intro to computer science courses in universities. It's good for sort of teaching the fundamentals of programming languages. The second Lisp dialect you'll see is called Common Lisp, and that's the actual production language out there, like running production systems. And so Clojure is a Lisp dialect that was made in 2007. So the first thing you notice when you're looking at a Lisp dialect is that there are parentheses in places we didn't really think parentheses belonged, right? So I have some Clojure code on the left and some C code, or just sort of any standard sort of Python code, whatever, on the right. And you'll see it's structured a little bit different, right? In this case, as you can probably guess, we're adding two numbers, right, 5 and 4, but we do them in a little bit differently in Clojure versus a C-like language. So in Clojure and in Lisp in general, everything is a list. And that's actually what Lisp stands for. It stands for list processing, L-I-S-P. And so parentheses are what's designating a list. So you can see we have a list there with 3 elements. The first, or the 0th element, is a plus sign, and then 5 and 4 are the rest of the elements in the list. And so the 0th element in a list is the function that you're calling. So in this case, we're calling the plus function, and then everything else in the list are arguments to that list. As you can see then when we, if we want to add more numbers, right, we just add more numbers to the list. So here we're adding 5 plus 4 plus 2, and we're getting back 11. So the main thing to take away from this slide is the 0th element of the list is the function that you're calling. So that's for calling functions. You can also define functions. So here, when we're defining a function, we're defining a function called q, using defn as the 0th element in the list. So we're defining a function called q. It takes a parameter n, and then we're returning n times n times n. So we're cubing the function. Then you can see once we evaluate this list right here, this defined function list, then we have this cube function available. So we can just call cube4 by putting cube as the 0th element in the list, and we get back 64. So I have some similar code on the right-hand side in C. And you can see there's one thing on the right-hand side that we don't have the left-hand side, and that's the data types, right? On the right side, we specify that we're taking in an int parameter, and we're returning an int parameter. We don't have that in Clojure at all. That's because Clojure is dynamically typed, which means we really don't have, we don't specify types, and we don't really even have them. So in this case, in the Clojure code, we are, that'll be running for anything that can be multiplied, right? So if you have like a double or a float, anything that supports the multiplication operator, you can pass that in and this cube function will work with that. So we have these sort of more general functions, more flexible functions, sort of at the expense of not getting some compile time safety, right? If you try to pass in, say, a string to the cube function, that's going to be a runtime error. So that's sort of a dynamic versus static language war that we're probably not going to solve tonight. But that's one of those ongoing conversations. So one of the benefits about Lisp is there's really not too much syntax, right? Everything is just sort of taking lists and nesting them together. So if you pay attention to how you call your, like what you call your functions, right, sort of the API that you're building as you're writing a program, you come up with really beautiful abstractions and domain-specific languages describe your problem. So here I have two libraries. You can probably tell what they do, right? That top one is for querying a database. It's sort of like sort of similar to ORM, right? It's Clojure code that will query a database for you. And on the bottom, I have it's called Composure, I believe, and that's for defining a web server, right? So you can see we're defining GET requests and POST requests, what our application responds to. So it's not too far a leap to see how you can combine these two functions, or combine these two libraries to make a really elegant web application that maybe takes data and inserts it to a database, selects database, returns strings. It's very cool to get going, and if we have time, I'll show a little bit of this running live to build a simple application. So that's what it means to be a modern Lisp dialect. And so next we're going to talk about what it means to be designed to be hosted. And this is one of the real strengths of Clojure. So Clojure is a little bit interesting. It doesn't really define its own runtime, its own VM, right? It just uses VMs that are out there existing already. So there's three main VMs it targets. It's the JVM, so Java, the CLR, which is .NET, and then there's the web, so running either via Node.js or in a web browser. It can do either. And so up front, you're going to choose one of these runtimes to run on and write your code for that runtime. And then when you choose that runtime, you can use any of the APIs or libraries that already exist out there. So if you find this really cool Java library, you can go ahead and use that from your Clojure code just natively. You don't have to have any like special wrappers. Same with the CLR. If you find you really like some DLLs that are out there, you maybe really like the .NET Microsoft API, you can use that from your Clojure code if you use Clojure on the CLR. And on the web, that's a little bit of a different case, right? On the web, Clojure compiles down into JavaScript. So you're writing Clojure, it compiles down into JavaScript, and then you can call any sort of web libraries you like. You can use jQuery, Prototype, Angular, any of those fun libraries out there. And then underlying all of that, you have the core Clojure API. And the Clojure API defines a couple of common, just often used libraries, like doing data structure manipulation, that sort of thing. Things that are the same across, they're pretty core concerns, but so you have a nice unified interface. You can use the Clojure API for some of the more common operations. So I have a couple of examples here I'm going to be showing. So if we're taking a look at the JVM, here's an example of using the Java APIs from the JVM. So in this case, we're just printing out some disk utility, some disk information. And so we don't really want to go and, I guess, we don't really want to go and like write that ourselves, right? We'd much rather use an existing API out there, right, that sort of handles some of the cross-platform concerns. So in this case, we're just importing just a java.io.file, right? That's right out of the Java SDK. Then we can actually just new it up in the middle of our code, right? We're pointing here at our directory root. And then we can just call Java methods right on that object, right? So we're calling getTotalSpace, which is defined in the Java API, calling that on our root file object. And we can also get the free space and go ahead and print that out. So this is just a little command line application that when you run it, it'll just print out both those. And hopefully it matches maybe what DF prints out. So that's Java. Any questions so far? All right, cool. Next we're going to go into JavaScript, which looks pretty similar. Here we're just using jQuery, writing a little index or a little HTML application, JavaScript application. So we just embed this in our application. Then when you compile it, it's going to spit out the JavaScript. So here we're getting a reference using jQuery to our body element, our body tag. And we're actually just calling a JavaScript prompt, asking the user to enter their name. They're going to go ahead and enter their name, and that'll be put in the name variable. And after that, we build up a greeting using some string concatenation. That's what str is right here. So then we get the string hello name, hello Will in this example maybe. And then we call the .text property, which is defined by jQuery, on our target and pass in our greeting. So this is going to take our greeting and put it in our target. And that's just the same exact sort of API you would use if you're using jQuery. So finally, we're going to talk about some of the concurrency constructs in Clojure. So Clojure has two main concurrency constructs that make running or writing multi-threaded code easier. It has atom and ref. And we're going to go into both of those very quickly. So atom is for atomically updating values. So when you have a multi-threaded code, you have a lot of concerns you might not see in normal single core code. So I have some sample code up here that shows a simple counter, right? We have a single static counter set to 0, and then you can call get next, and it'll just return the next version of the counter, right? So you'll call it once, and you'll get back 1. Call it again, you'll get back 2. It's just a simple counter. So that's fine in the single thread case. But once we start talking about multi-threaded code, right, this can get a little bit messy. If we have, say, 2 threads, both with a reference to the counter, they can both call get next, and they can both read counter as 0, right? Then they go back and increment counter in their respective threads and get back 1, and then they return 1. So in effect, we called get next twice. We got back 1 both times, right? We have a sort of race condition here. And the typical way you would solve this in a language like Java or C# or something like that is you'd have lock objects, right? You would surround all this in sort of locking constructs. And that's kind of tricky code to get right, especially once you get past this sort of a simple, like 3-line code case, right? So Clojure has something called atom. And we have our similar code here, right? We have our counter, but instead of defining our counter to be 0, we define our counter to be the atom of 0. And this atom is going to handle all of the locking code for us. It'll handle all the sort of retries if it fails to obtain a lock, all the sort of stuff that you're supposed to put in good locking code. Then you can see we have our get next function here. And then when we want to update our counter, we just call swap on our counter, swap out the values. And then we pass in the inc function, which increments our function. Inc is similar to sort of plus plus in your sort of more standard languages. So this is how you do multi-threaded code. And the neat thing about Clojure is that when you're doing code like this, there's really no mutation. The only mutation that's available is thread safe. So typically when you have a value, you have a variable, you're going to take that variable and maybe mutate it to change it around a little bit. Whenever you're doing that sort of mutation, you run into these potential multi-threaded issues. So Clojure prefers immutability, but then when you do need to do mutation, like sometimes you have an algorithm, or maybe it's easier to think that way to have mutation, you have these nice thread-safe constructs. One final, I guess the second concurrency construct is ref. And if you're familiar with databases, you know databases have the concept of transactions, right? You have a couple of concepts that you want to, you have a couple of operations you want to transact. If one of those operations fails, you want to have everything roll back and leave the system in a pristine state. And so ref is a similar concept, except it's transactions for your code as opposed to at the database level. So here we have a sample program where we have 2 collections, a files collection and a recycle bin collection. And you can say just put strings, maybe file names or something in these collections. But we never want to say delete a file from the files collection and try to move it to recycle bin, then have it sort of disappear. Maybe there was trouble adding it to the recycle bin, right? You don't want that just to disappear and all of a sudden not be in the files directory or in the recycle bin directory. You want it to always be one or the other. So you want the delete operation to be pretty much all or nothing. And that's what ref gives us. So similar to the atom call on the previous slide, we define our files collection as a ref collection. Our recycle bin collection is a ref collection. And then we have this doSync function here. And this doSync function is basically sort of like a begin transaction call, right? We're saying in our doSync block, we remove the file from the files collection and add it. That conj, C-O-N-G, stands for conjoin. It's how you add to a collection. you can join the file with the recycle bin. And so all of a sudden this is a transacted code, right? So if there's an exception thrown, maybe just, it could happen for any number of reasons, like out of memory exception or something like that. This do sync will roll back and it will not be committed, so you won't ever be in this weird state of basically in a state you don't want to be in.
If you get those in the right order, I mean, after you removed it, is it still there for you to conjoin to the recycle bin?
So in this case, we actually were passing it in here, a file, right? It's a parameter to our function.
Reference to it.
Right, so it's just a reference. So we can, you could swap if you wanted. It doesn't really matter in this case. But yeah, this will remove the file from the file directory and then add it to the recycle bin. So that clear things up a little bit?
I guess logically you do it the other way around, right?
Well, you have the file reference internally, right?
Yeah.
Right. So yeah, that points it's a pointer to the object, basically. Right? Although you could turn that around, maybe that would make more sense from a code reading perspective. All right, so that was just a quick overview of Clojure, right? We covered what it means to be a modern Lisp dialect. We talked a little bit about the hosting options that you have in Clojure, and talked a little bit about some of the concurrency. Oh, okay.
Their way is a little safer if for some reason your program crashed in the middle.
Doesn't matter.
That's what his.
It doesn't matter. It's a transaction.
Right.
If either one of them crashes.
But it is true. There could be something like maybe you completely just yanked the power cord or something like that, right? Something that just there's absolutely zero protection against, right? That way, you're probably right that you could go ahead and add to the recycle bin and then wipe the files.
When you say it's a ref, is it like a pointer, or I'm trying to figure out?
Oh, ref. Yeah, that's a little bit of a naming collision. Ref. It stands for. Referential. I couldn't tell you what it stands for, but it's not really related to like pointer references.
Well, because I'm wondering if everything, like you said, alter and then it has an object, can it be an integer, can it be anything, or is it defined only for certain types that can be, you have to rewind and add the undoable function?
Right. Yeah, so it can be an int or anything like that, right? It doesn't have to be just be a collection. It'll work for anything that, yeah, basically, as long as the types match up here, the operations that you're trying to do on it match up with the type, it'll go ahead and work for that.
So in the,
sorry, go ahead. According to Clojure.org, ref stands for transactional reference.
All right, thank you. Thank you.
in the classic sense of transactions where they're debiting one account and crediting another, those two things could be accounts in memory, right?
Yeah, right.
Subtract money from one account and add money to the other account. It wouldn't be half done.
That's actually sort of like the go-to example for ref. I struggled to come up with an example that wasn't like that. But that's it's a great use case for like withdrawing or depositing into accounts or transfers.
So where are you using conjoin?
Oh, right here.
No, I mean where?
Clojure.
Where are you using? What kind of application are you using it in?
So I generally use it for web applications, right? I don't use it in production right now. It's basically just something I'm playing around with on the side. I'm trying to sort of write an internet app and work in it. Just, for example, it's one of these applications that needs to have like sort of double book accounting, right? Just to be very exact. You can use it for web applications, command line applications, like pretty much anywhere you might be able to use Java, right? You can use Clojure. So you wouldn't really use it for like embedded or anything like that. It runs on the JVM and these sort of more heavy VMs. But pretty much anywhere you use C# or Java code, you could use Clojure. I think Groupon and Clojure, or Groupon and Netflix.
Yeah, Netflix is the big one.
Right. They're both historically Java shops, right? But they're really like using it and releasing open source libraries for it and that sort of thing.
So it's in heavy production in those two.
Oh, it definitely is in production.
Yeah.
Just not by me.
Netflix is hiring, like they're hiring majorly for their Clojure people. One of the Ann Arborites, Diane Marsh, who used to run SRT, works for Netflix, running a department of developers that do a Clojure development, and they're porting a lot of their stuff over. They get to take advantage of the JVM as far as speed, performance. multi-threaded and all that, but they don't have to write in the arguably archaic, list of lists.
Exactly.
Netflix actually is really good about giving back to the communities that they take from. They're really, if there's a Clojure bug and they find it, it will get a patch.
Right, they're actually releasing a lot of cool concurrency libraries as well, right? Because they just have concerns that like the rest of us don't even dream of, right? In terms of like parallelism and that sort of thing. So they're releasing a lot of very cool libraries in that area for Clojure. All right, so that's pretty much all I had. I have, how much time do we have? We have just maybe 5 minutes.
5 to 10 minutes of,
Okay.
Well, 10 would be really pushing it.
yeah.
Okay, all
Especially
right.
out the door by quarter 2.
Okay. All right, can everyone see that okay in terms of font size?
Yes, exactly.
Okay. Okay, so I have here just a very sort of bare bones project. So I'm using this line command, right? This line command is basically whenever you're interacting with a Clojure project, you're going to use a line command to do various tasks like run your application or build it, that sort of thing. So I'm going to go ahead and run this application in one tab. And then we can take a look at the source. So this is a simple web application, right? Right now it's just serving a single page, and that page content is hello mug. So let's go ahead and make sure that actually, I'm not lying to you guys.
May I have your attention, please? The time is 8:32. The library closes this evening at 9 o'clock. The internet connections will begin to shut down 10 minutes before closing.
A little bit of time, I'll go quickly. So this is our program right here. There's some stuff in another file that I'm just boring about, like sort of bootstrapping the server. I'm hiding that from you guys for now. But this is like the main application, right? We're defining our application routes, defining that when you do a GET request to the root, we're returning the page content, right? So you can see that when you go ahead and pull up the root, we do get our content.
So is that, I'm trying to follow, is this like a compiled thing?
It is compiled, right. So I can go ahead and, it's compiled, I have this run program going around in the background. But it's pretty quick compilation, right? I can change that there, right, and go back and it's changed there. So sort of the problem with that is that's reloading my application, right? It's saying, hello world, I go and change that and save, it's detecting a save and reloading the application. So that's not great. It works for these sort of like these little tiny applications, right? But if you have an interesting application, right, something that's big, you don't want to maybe reload your application every time you go through and want to just inspect something. So rather than running this standalone, I'm actually going to show one of the sort of historical powers of Lisp, which is the read about print loop. And this really powers a lot of your development process when you're writing an application. Okay, so this is the Clojure read about print loop. And so it just allows you to basically execute some Clojure code, right, get back a result. Pretty standard stuff. There's some nice stuff like being able to pull up function documentation, that sort of thing as well. I think you might also be able to pull up, yeah, the actual source of the function if you're curious, right? Nothing really too interesting there though in terms of a read about print loop, right? It's pretty standard functionality. But what we can actually do is go ahead and start our server from within the read about print loop. At this point, if I refresh, we should still be running, but this time from the read about print loop. So I'm going to go ahead and, we have our application here, right? We're in our namespace web.routes. I'm going to go ahead and switch to that namespace. And now we have a reference to all of our variables, right? I have this page content here. Go ahead and just page content. So the cool thing here is that now I can actually change things. I want to redefine page content, maybe back to hello mug, so I just went ahead and updated that. So now that did it without reloading the application. That time I just went through and reread the symbols after I redefined them. So I do have an example that proves that, where we build up like application with actual state, where we can add and remove things. Running out of time?
Yeah.
All right. So if you're interested, right, I think I'll show you the demo. I'll put this up on GitHub or something like
Right.
that. Sorry. No, that's fine. Any other questions?
Well, so you tinker with that, but then there's, like most of those, then you don't have a good way to get it back out, right? Like, I made the following changes.
Oh, yeah, yeah. Same as sort of using
This
like
was the good
the
change.
Chrome debugger or something
Yeah.
like that, right? Like it's neat for debugging and inspecting your application state. Like maybe checking out what's in your various data structures and stuff like that. You wouldn't really be writing entire functions in your redevelopment. Right.
I want a rebel diff.
All right. Thanks.
Yeah.